Okay, so here we are, we're on 2.2, and we are on page 48. We're just going to skip ahead for a little bit. We're going to work on the graphs, and then we will come back to the beginning of 2.2, where we will deal with acceleration and the kinematics equations. So right now, we're just going to work on the graphs, okay? So if we look at this dt graph, this position time graph, okay, what do you notice about the graph? First, what's jumping out at you? The curve, okay. So if a position time graph is curved, what do we know the motion is? Okay, so non-uniform motion. Okay. And would it make sense for a sprinter? Think about, what's that man's name? The gold medal, Usain Bolt. If you watch him, is he going to be as fast as he is at the beginning as he is near the end? He's picking up speed all the way till the end where he probably reaches some maximum speed. Yeah. Okay, so when we look at this graph, it makes sense to us. It's a sprinter. Now, when we go to look at the question, what it's asking for, it says use the graph to determine the sprinter's speed at 2.5 seconds. So what have they asked us for? Have they asked us for an average speed? Or have they asked us for a instantaneous speed? Is this a speed in the moment? Or is this a speed over the whole time? Speed in the moment, okay? Okay, so they are looking for at a specific instant. Okay, that is called, aka, instantaneous velocity. Oh, they just want speed. So instantaneous v with no bar above. To find instantaneous velocity off of a graph, especially a PT graph, what do you need? PT graph, how do you find speed? We just did it on the quiz. You need the, off a graph, you need the slope, right? DT graph, you want the speed, you need the slope. How the heck do you take a slope of a curved line? Doesn't make sense, right? So what you need is the slope of a tangent line. So that's what you need to find, okay? Find the slope of a tangent line at that point. Okay, I task you with that right now. Okay, so I'll get you started. Do you guys know what tangent is from math? Touches a curve once. Okay, so where's 2.5? Here's 3. So here's 2.5. So get in there at 2.5 and draw a little dot with your precise pencil. And then you're going to attempt to draw a tangent line. Do you see this? You see my line? Okay, right there, that's not tangent because it touches the curve twice. I just need to get that dot and that dot only. That's looking like a tangent to me. Okay? Now you find the slope of this line. So you got to find some perfect points. I'm thinking that this one's pretty good. Whatever you see fit. Okay? Maybe like this one here. Okay? So I'll task you with finding the slope of this tangent line. So we did a slope calculation of the tangent line at the specific instant, 2.5 seconds. We used data points on the line of best fit, and we have an approximation to slope. And when you do the slope calculation for a d over t, the change in y is meters, the change in x is seconds. You have your units meters per second, and it's asking for speed, so you don't have to give a direction. All right, let's move on. So I will let you guys do this one for homework. I'll give you guys, because it's very similar. Okay, it wants This time the velocity, not the speed. Okay, so put a underline or highlight that word. And just give yourself a reminder, don't forget about the direction. And it wants it at 1.5 seconds. Okay, so here's halfway between 2, so that's 1, so this would have to be at 1.5. It wants the slope of a tangent line right there. Now, which direction will this slope be? Down to the right, so you should have a negative slope, and that will tell you that, oh look, boom, it should be south when you communicate your answer. So I'll leave this one as exercise. When I did it myself, I got 8.3, so you can be more precise than I did. I don't even know how precise the book's answers are. So I'll let you guys try that one. Your slope of your tangent line should look something like this. Okay? Find some data points on there, and this is instantaneous velocity off a dt graph. Okay, let's take a look at question 36. The distance time graph below represents the motion of a sprinter running from a standstill and then slowing down to a stop. Identify the area of the graph. I wish it didn't say area, maybe portion or something of the graph where the sprinter is. Okay, let's figure these ones out. Let's start with the easy one, which is in the middle. This one right here. For a constant velocity, your dt graph should be linear. What portion, I don't know, just change that word area. Let's change that to portion or section. Maybe section would be better. What section of that graph looks linear to you? B. So this is where he's traveling at some constant velocity. Now, if you look at A and C, they're curved like a quadratic, the parabola shape. We just need to know if in part A is he speeding up, slowing down, or in C is he speeding up, slowing down, and use your knowledge of the tangent lines that we just did. What do the tangent lines look like? Let's start at A. Like, what would a tangent line look like right there? Would it be less steep or more steep than a tangent line up here? What about here? What about here? So draw some tangents. Quite steep, less steep, even less steep, and almost flat. And is this a sprinter? Is that what they're talking about? Right. So think about the real life thing. Sometimes in physics you get into the stuff, it almost confuses you. Just boil it down to simplicity. When you're a sprinter, you start off slow and then you pick up your speed, right? Look at those tangent lines. The slope of a tangent line on a dt graph would indicate its magnitude of speed, right? So less steep to more steep, slower to faster. And then what's happening over at C? Steep, less steep, less steep. So it's going faster to slower here. Okay, so for curved position time graphs, you need to analyze slopes of tangents, okay? So speeding up would be A, slowing down would be C. 37's in your appendix. This one's actually pretty easy, so I'll leave you guys this one for exercise. I'll leave this one for exercise, okay? Okay, question 38. You have a distance time graph. You have a lot going on, different sections of the graph, correct? You have a lot being asked of you. Speeds, distances, displacements, and velocities, okay? Some in a moment, some for the entire trip, okay? So I'm going to give you guys time to work on this one right now. I'll be walking around helping. Appendix A will be there to help you, okay? So we're going to work on this one together. Now, before we do that, the next page you see the CD here? You can do that if you want. The CD is in your possession from the workbook. That's up to you. And then there are a lot of questions still to remain. So let's pause there and let's work on this one together. Okay, so just confirm your work with mine. Let's talk about these. Okay, so at 5 seconds, determine the speed at 5 seconds. You want a slope of a tangent line right here, but I mean it's already linear here. So you basically just need the slope of this section. And it's almost 5 in 5, almost 5 meters in 5 seconds, so it's pretty much 1 meter per second. And you can see, look at the slope. Over 1, up 1, over 1, up 1, over 1, up 1. Basically, it's a little bit off. Okay? Now the speed at 12 seconds, these are instantaneous speeds, so we need a slope of a tangent line right here, and it's basically flat. So what is a flat tangent line? You know, essentially 0 speed. Okay? Now distance traveled in the first 20 seconds, this is just reading a graph. Find 20 and find 12 meters. Distance, you don't need a direction. Maximum displacement. Maximum farthest away from the origin, so I think that's up here. It's pretty much 19. It might be a little bit below 19. And because it's a positive 19, we assume that it's north. Now for average speed, and we're just going to jot this down again so you don't forget. V average is total distance over total time. And velocity average is change in position over time. Okay? So you're just going to have a meters divided by a seconds. You just have to be careful. For speed, you need total distance. So why do I have 34? Here's 19. Okay? Roughly, right? Roughly 19. What was this number? Roughly 4. So how far did you travel from 19 to 4? 15. 15 and 19 make roughly 34. Okay? Divided by the total time, which is right here at 31 seconds. Now for the velocity, you need the velocity average, you need the change in position over time. So after all this trip is completed at 31 seconds, where are you? Right here. This is 4 meters north of the reference point. So that's why I only have 4 divided by 31. And 4 divided by 31, keeping direction in mind, whatever this number would be, positive 0.13 meters per second north. Okay. This 4 divided by 31, maybe some of you are starting to make these connections. Look at this. What would the slope of that red line be? Would it be the same? Would the slope of that red line be the same as 4 divided by 31? It would, right? All right. So we're skipping this next question. And let's go into 40. Okay, so 40 is similar to the lab where you have to go from, or not the lab, the daily quiz this morning, or the start of the block. You're going to take these tangent lines that they've produced for you, and this is going to be an exercise for yourselves. And you're going to calculate the slopes of these tangent lines. And then you are going to record the velocities here. And then you are going to graph the VT graph. Okay? So on 40, please make these notes for yourself so you remember to do it. You have 3 slope calculations. And I will just give you some rough estimates. I got about 5.4, about 21.5, and about 31.25. So these are my sort of, I did this on my own last year. These, you don't have to have it exact. You have to have something similar. Now, what do you notice? As time is going on, the velocity is increasing, okay? So you are going to plot these data points, and you're going to do a line of best fit. I don't know, maybe your data points look like this, I'm not sure. And then you're going to do a slope calculation of a VT. And a slope calculation for VT would be delta V over T. So you have a change in velocity over time, and this will give you acceleration, okay? So V2 minus V1 over T2 minus T1, and you'll get yourself an approximation for the acceleration. So I got, when I used my data points, I got about 4.4. So you can attempt this question, okay? Again, we're just trying to practice our graphing, get used to what is what, right? We have a curved position time, and then a linear VT, and then from the linear VT, we calculate that slope to get acceleration. Okay, so we got to get to know these patterns. Let's flip the page. Okay, just another slope calculation. A slope calculation of a velocity time graph will yield acceleration. So please attempt this. Again, find some perfect points, practice your slope calculation. .42 is nice, it's in the appendix, so when you're doing this at home. So let's go, how about, I'll give you the last 5 minutes to try either 40 or 41. Okay, and we'll pick it off at 42 where we left off. We'll pick it up tomorrow. Okay.